generates some very strange patterns. And we explored all those parameters just to see if eventually some ALMA observation, some features in the ALMA observation could be associated with these kind of simulations. Also, in the early test, we did not include cooling, and this is the kind of shape we're finding, you know, these cubic spiral that was very strange and hard to understand. But was understood in a sense that there was some accumulation of heat that was released at specific phase. And when looking at the temperature was really too high, something like 10 to the 5. I mean, it's never been seen in these objects. So it's clearly some physics was missing, and we implemented some cooling prescription. And you see, when you include cooling, then you go back to a more a clear view that we can better understand with the formation of the spiral. Also, if you do not include cooling, well, the gas around the companion is behaving like more adiabatically, so it expands, so the mass cannot be accreted onto the companion. With H1 cooling, we see the formation here of the accretion disk. And we analyze, well, those disks, well, jolly. And so you see, well, this is where the matter fits the disk. We see there's some kind of spirals that developed. And if we look sideways, we see that it's a flare disk, and it's also asymmetric. We also analyze the velocity inside the disk. It follows clearly, well, nicely a Keplerian profile. And of course, we studied, well, the mass accretion disk and the disk properties depending on the parameters. Jolene went into a next step of complication. It was too easy before, so just to have a triple system. So in that case, there is the inner binary where there is the wind-emitting AGB star, and you have a tertiary companion that orbits the inner binary. And what we see is basically the superposition of these two spirals. You have the inner spiral with a smaller pattern. You can see here in the zoom in. And the tertiary pattern goes over those waves, and that's why it's kind of wavy shape that we see in the wake of the tertiary. Then, well, also implemented dust in this wind. At the moment, all the simulations I showed did not consider dust. And if you include dust, that impacts also the hydro. Okay, and it impacts the hydro because dust are opaque and absorbs radiation, and that can be converted into momentum, and that can accelerate the wind. This is, well, the mechanism to launch those winds in AGB stars. And so you have this radiative force, and if you combine it with the gravitational attraction of the sink, it can be recast into that formula where you see that gamma parameter that I mentioned earlier. And in case of dust and winds, this gamma is given by this formula, where you have the opacity of the gas plus the opacity of the dust times the luminosity. This is the photon flux, and eventually you also have some extinction of the stellar light. But dust is a different component. It does not necessarily have the same temperature as the gas, and if the dust and the gas have different temperature, you will have heat transfer between the two components, and that also generates some cooling or heating terms that should be accounted for in those equations. And if we want to treat the problem, the full problem, that we need to estimate the opacity and the dust temperature. For the dust temperature, there are some prescription that we included, some loosey approximation that can be solved using some simple ray tracing, but the best and most accurate way would be to use MC first, that would directly provide us the dust temperature and potentially also the radiative acceleration. So concerning dust, how did we model dust? So just the very basic picture is that we have a bunch of atoms, carbon, oxygen, that was produced in the AGB, and those atoms, they combine to form molecules. And some of those molecules are called monomer, and they are the building blocks of the grains. Okay, and here I'm just focusing on carbon-rich chemistry because it's easy and it's much better understood. And you have a first phase, which is the formation of that seed. And once you form, so this is the nucleation part. And once the seed is formed, and the seed is typically composed of 100 or 1,000 atoms. And then once the seed is formed, then you can grow. But you have to have that seed, because otherwise it's lowering some energy, otherwise it disperses, okay? And how do we do the growth? Well, so our dust is just pure carbon, composed of n atoms of carbon. And this is how we grow. We add C, C2, C2H2, or C2H. It's very simple chemistry. And then the grain size grows, okay? But to follow that step, we need to know the composition, the molecular composition of the gas. And this is what we do. So we store for each zinc particle the abundance. We follow the 7 elements, so hydrogen, CNO, and others. And we have a small chemical network that includes 25 molecular species, particular CO, the main ones. And so we solve at each iteration this chemical network, which is assumed to be at equilibrium. And then we got the abundances. And from that, we can go to the growth phase. So how do we model the growth phase? I won't go into the details because it's very complicated. This is the so-called moment theory that was developed by Gale and Sedlmayr. So instead of following the evolution of the grain size distribution, this is the one, we follow the moments. Just like in radiative transfer, we have the moments of the intensity. Here, it's the moments of the grain size distribution. And there are equations that tell you how those moments evolve. And it depends on those quantities. I won't go into the details, but all these quantities, they can be determined once you know the chemical composition, well, basically the abundances of monomers, and also the temperature and the density of your mate. And the beauty of that theory is that, well, from those moments, you can get the average grain size, typically proportional to K1 over K0. You can have the surface of the grain, K2 over K0. And K3 is the most important because it gives you the volume of your grain. And if you use the Mie theory, that can be related to the opacity in the small particle regime. So all this business, all these solving these equations plus the chemical network, just to get kappa, because this is the thing that we want. So this is the nucleation that we obtain. So this is the temperature, this is the pressure. And where the nucleation is high, that's where you form seeds. So the seed for the dust. And this is what Gale and Sedlmayr found in 40 years ago. So there is a very good agreement. And this is typically the trajectory of one particle. And it will go through that region of high nucleation. So that was implemented in Phantom, and you can see the impact of dust. So this is the wind profile. So this is various quantities as a function of radius. So this is the wind profile without dust. And when you include dust, so as you go away from the AGB, of course, the temperature drops. And eventually, if you drop below the condensation temperature, well, you start nucleating, forming dust, and you see the boost in the velocity. That's a very efficient way of accelerating. That's how it's accelerated in AGB stars. Right? And we see that we also follow the chemistry with H2, and this is the resulting opacity that you can see. And if you include this in a binary system, still to be analyzed, so you have the AGB, this is the companion, and you can see that the nucleation is quite high in the wake of the companion. So you can produce extra dust, well, not only in the wind of the AGB, but also in the wake of the companion. It can have some impact in determining the massless rates and other conditions. This nucleation scheme was also implemented into problems related to common envelope evolution with the group of Ursula De Marco in Sydney. And this is these are different snapshots of this common evolution. So the scale here changes from panel to panel. And so at different times, so there are the two components here, they get closer and so on. And what we can see is that very soon, after only a few years, you start forming dust. So this is the opacity, okay, a tracer of dust. And what we found in those simulations is that actually dust forms in the unbound material. So it's not going to help ejecting the envelope of the common envelope because the material is already lost. Okay. What we also show is that it forms very early. It's very efficient with our implementation of dust formation. And but the main impact will be on in the optical. The appearance of your object because of the dust will be completely different. And the last part of the talk will be dedicated to these colliding winds. So instead of having just one thing emitting some gas, now I consider that's at least two things at the moment that emit gas, okay, that emit a wind. So now we added some properties to the sea, well, the mass loss rate, the wind velocity, the wind temperature, so those initial conditions for the wind, as well as the resolution. You know, the mass, you remember that first formula, it depends on that resolution. And for those simulations, we need the acceleration mechanism, so this gamma factor. And in that case, in case of, so this is the simulation of Wolf-Rayet winds, colliding Wolf-Rayet winds. The acceleration is due to line absorption, photon absorption in a line of metals and scattering. That so you transfer the energy of the photons into momentum, and this is what drives the wind. And well, it's a complex theory, the CAC theory, where you should do radiative frequency-dependent radiative transfer, depending also on the gradient of velocity. Sobolev theory is very complicated, but there is a nice fit that can mimic all of this. And there is a parameter beta, and that beta parameter gives you this beta velocity profile. And this is the kind of things we observe. So this is for equal winds. This is the equipotential, the Roche potential. And well, the arrows trace, of course, the winds. And we see that, of course, they collide. And you have an increase in density in the meridional plane, just in between the two stars. But because the system is rotating and because of the Coriolis forces, well, this shock front will be distorted. Okay. Also, what we had to do, because you can reach very high temperatures, above 10 million degrees or so, so we had to add extra cooling in Phantom to deal with that, because otherwise that was not correct. But we knew that before, so that was good. So that's the work of my master student who did that this summer. And there is a very important parameter that describes the shape of those colliding winds, is this so-called cooling parameter, psi, which is T cool over the escape time scale. And basically what it says is that if psi is larger than 1, basically you have an adiabatic shock. So the pressure in the between the two colliding shocks is very high and is thermal, and that leads to a stable front. This is what you can see here. It's a thicker shock. It's supported by thermal pressure. And on the other hand, if you have a low value of that parameter, then the shock is radiative. So all the heat is lost. So it collapses because that removes the pressure support, and you get a very thin shock. And when it is thin, then it is subject to some instabilities. And we can already see that with decreasing parameter, we see that the flow becomes quite turbulent. We see that. And we analyzed in more details for the case of this instability. So this has been studied, and we did not discover anything. It's just the so-called thin shell instability here. So this is a zoom. It's quite high resolution. It's 5 million. So we only had to simulate the very inner part of the simulation. So you start with a relatively flat shock front between the two stars, and you can see it's in hours, quite rapidly those instabilities that develop, and they grow quite substantial. And in some cases, even one of these instabilities went into the star. So it was well, photon was crashing, didn't like it. What we did also is to analyze the mixing of that interface. So here we color in red the wind particle from the bottom sink, and in blue the wind particle from the top sink. And so you can see in that region the diffusion, well, the mixing of composition between the two stars. Okay. So that's what we've done so far. There are still improvements and are on the to-do list, on the wish list. Well, the first one will be to couple MC-FOSS with the dusty simulation, so we can get an estimate of the dust temperature, and also to generate observables. Also, potentially, MC-FOSS can give us the radiative acceleration, so we don't have to rely on other approximations. A very important aspect that was brought also with Camille is to include the oxygen-rich chemistry, because at the moment, this nucleation is just for carbon-rich, but most of the stars are oxygen-rich. So we're just probing a very small fraction of the star population. Another avenue of developments also concerns pulsations to get something more consistent, and we'll work with Owen, who gave a talk early this week on implementing some. We have already some ideas, and also with these wings, what we did, I didn't have time, but we also included rotation. So if you have rotation, then you have centrifugal forces that also distort the ejected material, and so this is included, but I didn't have time to show it. What Simon did also is that actually, rather than covering the entire sphere, you can just cover an angular sector, and this is what you can see here: the emission of a jet, well, a cumulated jet. There is no MHD, there is nothing. It's just the way you send particles, and this is actually what we see in a post-AGB in the systems via Hydra. So you have an AGB star, and you have the companion, and around the companion there is an accretion disk and jets. So we can, with these kind of things and some radiative transfer, try to understand better the observation. And also, well, gas dust coupling, which is also something interesting to investigate. So there's still a lot of work. I'm done. Thank you.
Thank you very much for the amazing talk. So questions? Here.
I had two questions. One is numerical, one is physical. Which viscosity prescription are you using in SPH? And the other question is, could we use the kind of prescription for the nucleation/growth that you use for the COPA in the context of protoplanetary disks to help like grow grains or even like nucleation?
Yeah. So concerning the viscosity, we just use a default setup, nothing specific. And I don't think that will play a strong role because, well, the wind is quite diluted. I mean, it's
not for the shock.
For the shock, yeah. Yeah, no, we just use the default setup. Yeah, just exploration. And for the nucleation, yes, that can be done. But as I mentioned, this nucleation theory only works for carbon-rich environment. And protostars are not carbon-rich, they are oxygen-rich. So I don't think that, unfortunately, that will apply. I should also mention that these nucleation implementation it does not include dust destruction. It's only growth. But this is a limitation at the moment.
So I have an observer's question. So cool physics. I like it.
Well,
Carbon-rich atmosphere, and you nucleate kind of in an amorphous way, I suppose, between 100 and whatever number of carbon atoms.
Mm-hmm.
Do these objects emit pH lines?
Well, you're the observer. You should answer that question.
that might help you to understand how it nucleates and how big they get in terms of the seeds or the molecule, the macromolecules.
Well, yeah, they do observe pH around those stars, but yeah, I haven't crossed the bridge to.
Because in your chemical network, because you have C2H2, that's one way to form pHs quite efficiently, actually.
Yes, yes, but at the moment here, it's a very limited network, and that's the approach of Camille to use these emulators, so we can also trace these complex molecules. Yeah.
There are questions?
Short question. In one of your plots, you showed like this interface between the wings of one star and the other.
Mm-hmm.
I was wondering if that could be the result of of the sampling you're using to place the wind particles? Because you mentioned the first slice that you.
No, yeah. You mean this concerning now, because here we changed the resolution, and this is something we've played with, and this is very high resolution. Here it's I think it's more than 8,000 particles per sphere that we eject.
Oh.
It's very, and we end up with more than 5 million particles. So we had to treat. We do not model the entire system, just the interaction region. And that was very reproducible. We did, of course, some conversion tests. Yes. Okay. There's one thing that we could not find, and that may be related to the kernel, is that depending also on the wind velocity, because here it's a simple case where the two winds have the same velocity, but if one wind is faster than the other one, it will bend the shock, and eventually the flow that goes along the shock can generate some Kelvin-Helmholtz instabilities on top of, well, if you have the Finchel instability, it wins. But if this one does not develop, then you can have potentially some Kelvin-Helmholtz. And we could not find any Kelvin-Helmholtz instability. So that may be related, I had discussion, maybe related to the kernel.
You need at least M5 kernel to get the Kelvin-Helmholtz. With M4, it's really like damp the edge of the
yeah. This is what
paper
last question, please.
Thanks for the nice talk. I have a question on the method of moment you use on the gray size distribution.
Yes.
Do you need to close the system? Do you need to approximate the shape of the size distribution?
It's a very complex paper. Those papers by Gaël and he wrote the book that thick, just filled with formula. Does he assume any grain size distribution? No, I don't think so. I don't think.
This system of equation is closed.
Yeah, but eventually, I think at some point he developed you can go even higher because this is limited to the small particle limit, so the Rayleigh regime. But if you want to include scattering, then you would have to go to higher orders as well, which is not included. But yeah, no, I think it's closed. Well, from what I understood.
Thanks. Okay, let's thank again.
Thank you.